Lubrication system. Function of oil. Review. Function of engine oil. If an oil serves the engine adequately, it must perform the following function. 1. Lubrication. 2. Cleaning. 3. Protection. 4. Cooling. 5. Sealing. 6. Shock dampening. 7. Hydraulic action. Lubrication. The primary function of engine oil is to lubricate moving parts. The oil forms a film between metal surfaces, preventing metal-to-metal contact and reducing friction. When the oil film is not sufficient to prevent metal-to-metal contact, the following occurs. 1. Heat generated through friction. 2. Local welding occurs. 3. Metal transfer results in scuffing or seizing. Cleaning oil acts as a cleaning agent in the engine by flushing contaminants from critical component. Sludge, varnish and oxidation build up on the pistons, rings, valve stems, and seals will lead to a rapid engine failure if not controlled by the oil. An oil formulated with the optimal additives will hold these contaminants in suspension until they are removed by the oil filtration system or during the course of an oil change. Protection. Oil provide a protection barrier, isolating non-like metals to prevent corrosion. Corrosion, like wear, results in the removal of metal from engine parts. Corrosion works like a slow-acting wear mechanism. Cooling. Engine require the cooling of internal components that the primary cooling system cannot provide. The lubricating oil provides an excellent heat transfer medium. Heat is transferred to the oil through contact with various components, then transferred to the primary cooling at the oil cooler. Sealing. Oil acts as a combustion seal, filling the uneven surfaces of the cylinder liner, piston, valve stem, and other internal engine components. Shock dampening. The oil film between contacting surfaces provides cushioning, and shock dampening effect is essential to highly loaded areas such as the bearings, pistons, connecting rods, and gear train. Hydraulic action. Oil acts as working hydraulic media within the engine. Examples of this are the use of oil to operate the engine brakes and STC injector tappets. Engine oil must be formulated in such a manner that it does not foam as a result of the mechanical agitation processes associated with its many functions. Foamed oil results in engine damage similar to oil starvation due to insufficient oil film protection.
Oil plays a vital role in engine operation and lifespan. Engine oil's 4 primary functions include lubricating, suspending contaminants, dissipating heat, and acting as a hydraulic fluid for internal engine components. Lubrication represents oil's primary function. Inside the engine, moving parts generate friction. Oil reduces friction between these surfaces by creating a narrow film of oil molecules. This oil film reduces friction and heat. Oil also isolates and suspends harmful contaminants between oil changes. By suspending these particles, every oil change flushes this damaging material out of the engine. Oil also protects against rust and corrosion by coating all internal engine parts, preventing oxidation. As oil flows through the engine, it also removes heat from friction points isolated from the cooling system. Finally, vehicles use oil as a hydraulic fluid, engaging such components as VTEC rocker arms, VTC actuators, and the cam chain tensioner. In order to lubricate all the moving parts of the engine, all oil systems use common components. A typical system uses a pump to move pressurized oil throughout the engine, and then gravity returns oil back to the engine's sump to circulate through the engine again. In this section, we'll review these components. The lubrication system uses a positive displacement oil pump to pressurize engine oil passages. Some pumps mount at the front of the crankshaft, while other engines drive the pump using a chain connected to the crankshaft. The pump assembly includes a relief valve designed to limit total system pressure. The relief valve opens if oil pressure exceeds spring pressure due to extremely low temperatures or a blockage in the oil passages. When open, the relief valve directs oil back to the oil pan. From the oil pump assembly, oil flows to an oil filter. Inside, filtration media traps contaminants such as dirt or metal particles. If allowed to circulate in the oil system, these contaminants can cause wear on the bearing surfaces of the engine. Contaminants may be the product of combustion or an internal contaminant. Products of combustion include soot, carbon particulates, unburned fuel, and water. When oil remains in the engine too long, these contaminants overload the oil's ability to handle them and forms a coating called sludge. This sludge covers internal engine parts, blocks the return path to the oil pan, and reduces lubrication performance. Internal contaminants consist of metallic particles, spent oil additives, sulfuric acid, and nitric acid. These contaminants increase wear on moving parts, leading to greater friction, reduced oil pressure, and component failures. Some contaminants can plug the media inside the oil filter. When this occurs, the oil filter allows less oil to flow to the engine and reduces oil pressure. To prevent a blocked filter from starving the engine of oil, the oil filter includes a bypass valve. Should the filtration media block too much oil flow, the bypass valve opens, allowing unfiltered oil past the blockage. While the oil filter removes solid contaminants from the engine crankcase, the positive crankcase ventilation, or PCV system, removes gaseous contaminants. These contaminants include combustion gases that leak past the piston rings and water vapor formed through condensation. The PCV system draws in filtered air and uses engine vacuum to send crankcase vapors into the combustion chamber. This reduces sludge formation and helps increase engine oil life. Some engines use an engine oil cooler at the filter to transfer heat into the cooling system. One coolant line delivers coolant to the oil cooler, while a second line sends the coolant and heat into the engine water jacket. From the oil filter, engine oil travels through oil passages. Manufacturers machine each engine part so that oil passages match up from component to component. Because of this, always consider oil passages when positioning gaskets during engine assembly. In some cases, an oil passage includes an oil control orifice. This device reduces oil flow when installed in an oil passage. Whenever you disassemble an engine, keep track of these orifices. If you replace a block, be sure the new block has the correct oil control orifices, or transfer the orifices from the original block to the new engine before reassembly. Most oil passages end at a bearing. Bearings typically include a wear surface on the rotating component and a bearing surface. The bearing surface may be a machined surface on the component or a replaceable bearing shell. Between the two components, a tiny gap allows a narrow film of oil to isolate the parts. To deliver oil to this gap, bearings include a hole in their face. From this delivery point, oil fills the space between the shaft and bearing. From here, oil drains from the bearing edge and returns to the oil pan. As the oil flows from the friction surface, it removes heat and impurities. When assembling engines, make sure the oil hole in each bearing correctly matches the oil passage. If an oil passage on the bearing is in the wrong location, no oil flow occurs and the bearing will fail. A few oil passages end with oil jets, located on the block underneath the pistons. These oil jets spray oil into the cylinder to lubricate the cylinder walls and cool the piston bottom. The final system component is in the cylinder head, where oil passages feed oil to cam control solenoids. When energized, the solenoids hydraulically operate VTEC pistons or a VTC actuator. Oil system faults include oil leaks and pressure problems. Oil leaks occur due to faulty mating surfaces, defective seals, and cracked or porous engine castings. Oil pressure problems include low pressure caused by wear, low pressure from low oil levels, or excessive pressure readings caused by oil system blockages. Problems in the oil system start with the basics. For instance, the correct oil fill level is critical for proper oil system function. Too much oil can interfere with crankshaft rotation. This can aerate the oil, leading to low oil pressure and possible engine damage. Excessive oil can also cause idle vibration, power loss, or even limit engine RPM. Finally, excessive engine oil may increase crankcase pressure, forcing oil out of the engine through seals or gaskets. Low oil level causes different symptoms. Hard braking or cornering can expose the oil pickup, drawing air into the oil pump and dropping system pressure. A low oil fill also reduces the system's ability to dissipate heat, increasing overall crankcase temperatures. For all of these reasons, always check the engine oil level before further troubleshooting.
Other topic to be discussed soon. 1. Engine oil flow review. 2. Oil viscosity. 3. Oil performance classification. 4. Engine fuel flow review. 5. Cooling system review. Please like, share, follow, and subscribe to my YouTube channel. Thank you.